We need to communicate science using words, obviously. And words, as versatile as they are, have their limitations. Descriptive words like fast, heavy, strong, or large are fuzzy, inaccurate, and not at all scientific. Here's what I mean. Let's say I think I'm a pretty fast runner for a writing instructor. On a good day, I probably am faster than the average teacher. But what does fast mean? A scientist, or even a track coach, would want to quantify that. Just how fast am I, and compared to whom or what? Numbers are the right tool for the kind of specificity needed here. Much better than the word fast, which doesn't mean much unless we have a point of comparison. So let's do a little comparing. The teacher, with a top speed of 24.5 kilometers an hour, might be correct in thinking he's fast when he compares himself to other teachers. But the word fast no longer applies to him when making a comparison to, say, a jackrabbit who has a top speed of 64 kilometers an hour. Or a cheetah, who's even twice that fast, which is to say nothing of other fast-moving objects like a raptor. Sorry, not that kind of raptor. No, not even that kind of raptor. The Lockheed Martin F-22 Raptor, which at altitude tops out at 2,414 kilometers per hour, about 100 times faster than that quote-unquote fast writing instructor, who at top speed looks like he's standing still in the Raptor's rearview mirror. Numbers are great for recording things accurately and comparing, like that a jackrabbit is more than twice as fast as a human, and a cheetah is about 5 times faster than a fast human. But numbers also have a drawback when communicating research or results, especially to non-scientists. A lot of numbers are very difficult for people to grasp mentally, especially if they fall far outside the familiar human scale. So, for example, that F-22 Raptor, if you were discussing jet propulsion and wanted to inform your audience just how fast fighter jets currently fly, you can give them a number that's accurate, 2,414 kilometers per hour. But that number out of context like this is going to be very difficult for your audience to understand. Given that people usually drive somewhere between 50 and 100 kilometers per hour in their cars, they'll know that 2,400 kilometers per hour is fast by comparison. But that number won't mean all that much to them beyond really, really fast. This is a point in your paper or presentation where you need an effective strategy for describing difficult numbers in a way that makes sense to your audience. We have a couple techniques to help you communicate numbers like these in a way that helps your audience to understand them. Let's continue to use that example of the F-22 Raptor. The first strategy to help you communicate how fast the F-22 flies is a comparative calculation. A comparative calculation uses that accurate number, 2,414 kilometers per hour, and it gives the number a frame of reference so that the audience can process what that number means. We can compare the F-22's speed to other planes. And perhaps the best place to start would be with a plane that most of the audience would be familiar with, the most popular passenger airliner in the world, the Boeing 737. The F-22 is going to be much faster than a commercial plane, so it would also help to put the F-22 into better perspective by comparing it to the fastest plane ever, the X-15. Those sentences might go something like, the F-22's top speed of 2,414 kilometers an hour makes commercial jetliners look sluggish by comparison, topping out at over 2.5 times the cruising speed of a Boeing 737. That blistering speed, though, seems modest when compared to the fastest manned plane ever, the North American X-15, which topped out at over 7,200 kilometers per hour, 3 times the speed of the F-22. Now the audience has a better sense of what 2,414 kilometers per hour means with regards to being a quote-unquote fast plane. Much faster than anything they've ever flown in, but much slower than the fastest planes can go. Comparative calculations are very useful for building a frame of reference like this. But that's not all comparative calculations can do. Let's see if we can do even better by putting these comparative calculations to work. Remember that the point of writing is to connect with the reader or audience. And one thing that people can conceptualize very well are images. So how can we find a way to turn that large, abstract number into a much more concrete image in the reader's mind? Instead of just comparing the speed of these planes to each other, we can use a benchmark, and preferably something that the reader can visualize or imagine. In the case of the airplanes, I'm going to use a trip around the world. How fast would it take the aircraft at top speed to circle the equator completely? This isn't that difficult a calculation if I can do it. You only need the circumference of the Earth in kilometers, and then you can simply divide that number, 40,075 kilometers, by the plane's speed in kilometers per hour. Then we can compare the duration of the journey for the planes we want to compare. Here are a few sentences that help to create an everyday image for the speed of the F-22. At top speed, the F-22 Raptor would circle the Earth in 16.5 hours. For perspective, if the Raptor took off on the same journey at the same time as a Boeing 737, the Raptor pilot could land, get a full night's sleep, and spend another entire 24 hours waiting for the passenger jet to finally arrive. Compared to fighter planes of earlier eras, like the 1934 Boeing Stearman 75, the Raptor would make the flight and then collect a week's worth of dust in the hangar before the older plane finally arrived. Numbers like 2,414 kilometers per hour are very difficult to conceptualize without adding context to help your audience. Using comparative calculations, especially ones that make use of easily visualized benchmarks, will help your audience to appreciate these difficult-to-comprehend figures. Here are a couple example sentences without, and then with their comparative benchmarks for comparison. The world's largest tree, the giant sequoia General Sherman, is estimated to weigh an incredible 2 million kilograms. Now, the same sentence with a benchmark for comparison. The world's largest tree, the giant sequoia General Sherman, is estimated to weigh an incredible 2 million kilograms. Roughly the equivalent of 60 fully loaded cement trucks. Here's a different example. The thickest of the ultra-thin second-generation solar cells are about 10 microns thick. Now the same sentence with a benchmark. The thickest of the ultra-thin second-generation solar cells are about 10 microns thick, which is about as thick as a single sheet of plastic wrap. In addition to difficult numbers, there are other description points that can benefit from visual imagery to help an audience understand abstract or complex ideas easily. Complex processes are very common areas of confusion for an audience, often because writers struggle to convey complex processes clearly. Fortunately, there's a helpful tool that you can use to describe complex processes, the simile or metaphor. As a writer, you can think of metaphor as a cognitive tool, a shortcut from one concept or situation the reader already understands to a new, similar idea you're trying to help them learn. And, just like benchmarks, metaphors that help your audience form a visual image of the process you're explaining are going to be extra powerful. First, though, I'm going to explain how a solar cell works, and I'm going to do it without the aid of any metaphors. We'll see how well that works. A solar cell is made by adding impurities to silicon, usually negatively charged phosphorus and positively charged boron. Placing this collection of atomic elements tightly into an electric field places these atoms in an orientation that is prone to releasing electrons. Then, when this electrical field is exposed to sunlight, the energy of the photons causes electrons to be released. These electrons are then channeled into electrical wires that transport the electricity to the electrical grid. That's not a terrible explanation of a complex process, but it also doesn't necessarily create a clear picture of this process in the audience's minds. Now I'm going to use metaphor to generate a clearer picture of the process. A solar cell is made by adding impurities to silicon, usually negatively charged phosphorus and positively charged boron. Packing this collection of atomic elements tightly into an electric field places these atoms in an orientation that is prone to shedding electrons. It's a bit like racking together a cluster of atomic billiard balls. Then, when this cluster gets exposed to sunlight, the light photons act like the cue ball, knocking electrons free. These freed electrons are then channeled into electrical wires that transport the electricity to the electrical grid. The obvious metaphor in this second version uses a visual image most people will find familiar: the cue ball knocking another ball loose from a cluster of subatomic particles. Of course, as with all metaphors, it isn't exactly analogous to what happens when photons strike a solar cell, but it's close enough to convey the idea in a clear manner that helps the reader to better understand the process. And that's actually not the only metaphor in that updated explanation. Metaphors don't always have to be as long and drawn out as the cue ball analogy. In fact, most metaphors are embedded in words we commonly use. So much so that lots of the metaphors we commonly use go unnoticed. Did you catch that second metaphor? It comes at the end of this sentence. Packing this collection of atomic elements tightly into an electric field places these atoms in an orientation that is prone to shedding electrons. Shedding, in the phrase shedding electrons, is a single-word metaphor that implies that these atoms releasing electrons is as natural as a dog getting rid of its winter coat. And it only takes one word to set up that implication. Here's a much more overt one-word metaphor that also generates an image to help explain how sunflower plants can be used to clean up toxic soil. The key to the soil cleanup capacity of sunflowers is their need to pull water and nutrients from the ground. Just as humans and other animals need to eat enough calcium, potassium, and other essential elements and molecules to keep their biological systems running smoothly, plants also need the same sorts of materials to make proteins, enzymes, and other cell components they need for survival. Surprisingly, though, plants will take up the ions of toxic heavy metals too, even radioactive ions that have no known biological function for the plants. This occurs because the gatekeepers of the root membranes of some plants aren't very picky and will let most metal ions through as long as they have the right charge. In this case, the word gatekeeper denotes one of the functions of the root membranes to sort which molecules stay outside in the soil and which molecules the root membranes allow into the plant. One could conjure the image of a bouncer who lets everyone into the club, as long as they have the right charge, and ID, of course. So you can see in these last two cases, metaphors don't have to be drawn out to help convey a clear picture of a complex process. All three of these techniques, comparative calculations, benchmarks, and descriptive metaphors, are effective tools in your writer's toolbox. And they're particularly effective at clearly conveying difficult, abstract, or complex information in an accessible and memorable way. Using these tools at description points in places where your audience may struggle to grasp a difficult concept will help you to connect with your reader. And now that you know what they are, look for these description points in your favorite science writing. You'll see these three techniques at work in the articles and presentations of the best science writers all the time. And now that you know what these writers are doing and how easy it is to learn to apply these skills at description points, you too can communicate difficult concepts vividly and easily in your own writing.